So the next section is about binary search tree. I think if you know already about the binary tree, so we can also have some basic understanding. So this is about the binary search tree, and we are going to look at how the binary search tree works and what is the insertion and deletion. So the most common operation in the algorithm and the data structure is insertion and deletion. When you insert, when you delete, so what is the performance? Okay. In your team project, that's also important. Whenever you have the data, how you insert, how you delete, and then how you perform the algorithm. Okay, so that will be the most important thing in your team project. That's why most of the team, I ask you to write the code from scratch. Okay. From scratch means you cannot use any library. Do not use any library. For example, I think some of you try to use like the machine learning. For example, you want to use k-means. Yeah, you can use k-means, but k-means already available and you can just reuse it. So I don't recommend this one. So this is not a good algorithm for you because I want you to write the code from scratch. Let's say I'm going to use the linear regression. Okay, if you want, write the linear regression from scratch. So I want to know how the linear regression really works. Not just calling the sklearn, import sklearn something 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 this one. This is no. Okay. So I will not accept this kind of import function in your in project. So you need to write the code from scratch. So I want to know, yeah, like what you already learned from here, the dictionary map as map. So they have the function from scratch, so you can reuse it. So now we are looking at the binary search tree. From the name, you know about tree. Okay, so we learn about tree with the video recording. Okay. So let's see the details about the binary search tree. Before we do the binary search tree, we need to understand what is the total order relation. So the total order relation, it is mathematical concept, and we usually use this symbol less than or equal to. They have three properties. Okay, so the first property is this one. X is less than or equal to X. So because this is reflexive properties. So if X is the same with X, okay, so we can just say something. The second one, we call it anti-symmetric property. So for this anti-symmetric properties, we have X is less than or equal to Y, and Y is less than or equal to X. If this one is true, then we can say that X is equal to Y. We have another property, we call it transitive property. So the transitive properties is x, which is less than y, and y is less than or equal to z. So it implies that x is less than or equal to z. Okay. So using this total order relations, there will be a lot of way to deal with the data structure and the algorithms. So still we are using the map, but now we are assuming that the keys is from the total order. So if you look at the dictionary that you learn in the Python, so the dictionary actually, it is only the key and value, and the key is random, or the key is not in the order. So the key in the dictionary, key is not in the order. Now, with the binary search tree, we assume that it is ordered. Order means we have a sequence. So 1, 2, 3, 4. It is order. And the keys are assumed to come from a total order. So the total order is from this one. And items are stored in order by their keys. So if we have items, then it will be saved according to the key. This allows us to support nearest neighbor query. This is the basic idea of the algorithm. If you already learned the machine learning, we have K and N. K nearest neighbor. So that is using some kind of key. So item with the largest key less than or equal to K, and item with the smallest key greater than or equal to K. So we try to look at this one, whether it is the largest or it is the smallest. So you still remember about the binary search. So the binary search can perform the nearest neighbor queries on an order map. So we call it, there is an order map that is implemented with an array sorted hierarchy. So it is similar to the high-low children game. So each step, the number of candidate items is half, and then it will be terminated after O log n step. In this case, it is already in the order. It's already in the order. We have 0, 1, 3, 4, 5, 7, 8, 9, 11, 14, 16, 18, and 19. So the final goal is find set. So we will half this one. If it is half, then we will check. Where is 7? 7, it is less than 8, or is it higher than 8? Since 7 is less than 8, so we will consider this array. So we have L, we have M, we have X. It is the low, this is high, and this is the mid value or the middle value. If we have this section, then we need to determine the L, which is the low, and the X, which is the high, and we need to determine the M, which is the mid. And then again, we have M, which is 3. So we need to find out where is 7. 7, is it less than 3 or is it higher than 3? We know that 7 is higher than 3. So we just focus on this side. So this is the new low, this is the new high, and this is M. So after we know the M, we need to check where is 7. 7 is less than 5 or 7 is higher than 5. 7 is higher than 5. And this one will be the last value or the last set to solve. So we can use this binary search in the table. We call it search table. So this search table is an order map implemented by means of a sorted sequence. So what we saw before, this is already sorted. And this is a sorted sequence in a map. We store the items in array-based sequence sorted by key. So we assume that the key, this one is key. This is key. This is the key, and so on. And we use an external comparator for the keys. External comparators means you can use the like simple this comparison and so on. So the performance, when you want to search a value, then it will take O log n time using binary search. If you are going to insert a new item, then it will take On. Since in the worst case, we have to shift n divided by 2 items to make room for the new item. And if you remove an item, takes On time. Since in the worst case, we have to shift n divided by 2 items to compact the items after removal. So this tree always the one that you need to consider. So in your team project, whenever you do the big O analysis, you need to do the big O analysis for 3 functions. Insert and delete. Okay, what is the big O for every of these one? The lookup table is effective only for order maps of size or for maps on which search are the most common operations. So if you're doing a lot of search, this is good. While insertion and removers are rarely performed. So for example, the credit card authorization. So if you have function to check whether the credit card usage it is not fraud or fraud, then you can use the search table. It will be very optimized. So when you do with the map, if you still remember, we have the standard map method, MK. Means we will return the V value associated with PK in map M. So it will show the value if the K exists. If the K does not exist, then it will raise an error. MK equals to V. So the associated value V with the PK in map M, it will replace the existing value if the map already contains an item with key equal to K. And delete MK means we want to remove the K from the map M or from the dictionary. If M has no such item, then raise key an error. The sorted map ADT includes additional functionality. It guarantees that an iteration reports key in the sorted order. So it is already sorted. sorry. And it spots additional search such as find greater than key, find GT. GT means greater than. Or we can find range. Find range. So we have number. What is the number of the starting point? And what is the number of the stopping point? And we can also do like this one to search any number. So the binary search tree, we will use the binary tree. You still remember binary tree? Binary. We call it binary because there will be only two children. Okay, at most two. Binary, we call it two. This is the left and right. So binary search tree is a binary tree storing keys or key value items at its nodes and satisfying the following properties. So U, P, and W are three nodes such that U is in the left of subtree. Okay, U is in the left of subtree V, and W is on the right subtree of V. So we have U, we have W. This is on the left. This is on the right. And the key of U, it will be less than or equal to the key of V, and the key of V will be less than or equal to the key W. So the key of U will be less than or equal to the key of V, and it will be less than or equal to the key of W. External nodes do not store items. Instead, we consider them as node. If you still remember on the tree, we have the external node. This is the external node. So if we want to put it as a tree, so we will do something like this one. This is example. Let's say we have 6. Okay. Then this left, this key should be less than 6. And this key should be higher than 6. So we have 2. And this one should be less than or equal to 2. This key should be higher than or equal to 2. And this one should be less than or equal to the upper side. We can perform the in order traversal. You still remember? Okay. In order traversal, we want to visit the keys in increasing order. So it means I will visit 1 and then 2 and then 4 and then 6 and then 8 and then 9. So when we do the search, okay, we can use the tree search, what we already learned in the binary search. To search for a key K, we trace down a downward path starting at the root. The next node visited depends on the comparison of K with the key of the current node. If we reach a leaf, the key is not found. So if we reach this one, then it means the key is not found. Now, let's find 4. Okay. We want to find the tree search. We want to find 4 from 3. So this is the algorithm. there are three sets. We want to input the three, and then the P, this is the map, and yeah, what you want to check on the tree. So K is the value. So if K equals to the P dot key, so this is the map. So if K equals to this one, then return P. So it means success. If it is not, then we can do something the same like what we did on the in order chromosome. So in order chromosome, we will check on the left section first. If the K is less than the P key and the T left P is not known, then let's do the three sets. So we will do the recursion. So we have T, and then we call the left of P, okay, the left of P is one, and again we still put the K or the number that we want to find, which is 4. Okay, so now we have in this position. So we go again this one, K equals to the P key. Okay, so let's say we want to find 4. So 4, it is the same with the key. 4 is the same with 2. No. Then let's check this one. 4 is less than the P key. P key is 2. 4 is less than 2. No. Then we go to this one. 4 is higher than P key. 4 is higher than 2. Yes. And T right P is not known. Okay, this is not known. And we go to the three search T right P, which is this one, and K. K is the number that we want to search. So we go back to these three sets. Now P is this one, and K is a value that we want to search, which is 4. So 4 equals to P the key. Yes. Okay, then we find this one. What about if we want to insert? If we want to insert, we need to perform the operation put K, comma O. So we can search the key K using the three search. Assume K is not already in the tree. So if K is already in the tree, there might be another process. And let W be the non-leaf reached by the search. So let's have a new leaf node, and we assume that this is W. We insert K at node W. We insert any K value into the node W and expand W into an internal node. Okay, I hope that you still remember. We have internal node and we have external node. Okay. So what is external node? We call external node as leaf. Leaf is this one. Leaf. What is internal node? Internal node, it means node that is not leaf. So this is internal node. This is internal node. Okay. Now we want to insert 5. Let's see about this tree. When you have this tree, so we want to insert 5. How to insert 5? So we need to know that 5, what is the properties of a binary search tree? The property is the key of U should be less than or equal to the key of V should be less than or equal to the key of W. So if you want to insert 5, it means we need to find where is the position of 5. Let's start from the root. 5 is equal to 6. Was no? Then, okay, we need to check. 5 is less than or equal to 6. Yes. Then we go to the left because it is based on these properties. If it is less than, then we go to the left. Now, in this case, we will check 5. Is it less than 2? No. So we need to check. Is 5 is higher than 2? Yes. So we go to the right. Now we are in the fourth. 5 is less than 4? No. And then we need to check 5 is higher than 4? Yes. So we go to the right. And we have a node here. And this node will be expanded. So we call this is expanded, the node. So 4 will be expanded into a new node, which is 5. And after we expand to 5, we put additional external, which is node. So this is the mechanism for insertion. So this is the algorithm for inserting into a tree. So the algorithm tree insert, where we have the tree, and then E is the K, and the V is the value. So a search key K to be associated with value V. So we have T, which is the tree search T, comma T to root, comma K. So we want to insert the K. Now K, we need to check whether it is the same with the key of P or not. Then if it is the same, then let's P value to V. But if it is not, go to the left. And if it is not, go to the right. Okay. So this is going to the left. And this is going to the deletion. So in the deletion, we want to remove. So before we remove it, we need to search where is K. So assume K is in the tree and let D be the node storing K. So if V has none or leaf child W, this is leaf, like this one, we can remove V and W from the tree with operation remove external. So we need to remove the external node, or we remove the leaf. After it's remove W and its parent. Now let's suppose I want to remove 4. So we need to search where is 4. At the first time, of course, we need to check whether 4 equals to the root. 4 equals to 6? No. 4 less than 6? Yes. Then we go to the left. Okay. 4 equals to 2? No. 4 less than 2? No. 4 higher than 2? Yes. So we go to the right. Now 4 equals to 4? Yes. We remove 4. When we remove 4, it means 5 will go out. So 5 will be the right node or the right child node of 2. So 5 will be the right child node of 2. And this W should be also 3. That's why we will have a new 3, something like 5 with 2 additional external nodes. Now let's say if I want to remove the key K, which is stored at node V, whose children are both internal. What does it mean? Internal. So the nodes, like this one, they have children. So in the previous one, the node have only one children. The other children is on leaf, which is no. But if the node have two children, okay, so we find the internal node W that follows V in an order. So we need to check the in order traversal. We copy the key W into the V. So we need to put the key W and we remove the node W and its left child, which is must be a leaf, by means of operation remove external. Now, suppose we want to remove 3. So this is the tree. So we have 1, 3, 2, 8, 6, 9, 5. If we perform the in-order traversal, you still remember? In-order traversal means I want to see from the smallest number and then it goes to the left. So it goes to the left, it goes to the left, and then this. So it means we will go from the smallest into the highest. Now we want to remove 3. So we start from the root. 3 equals to what? No. 3 less than 1? No. 3 higher than 1? Yes. So we go to right. Now we have 3 equals to 3. Yes. Because 3 equals to 3, so we want to remove this node. V will be removed. If we remove 3, what happens? If we put directly 8 into this one, it will not following the rule. What is the rule? If 8 into this one, so it means we have 1, and then we have 8, we have 2, and we have, so we have 8, and then how to determine the 6 and 9? So it is not possible. And then how if we put 2? If we have this one, and we have 3, so we remove 3. So now let's say 2 is here, and then we have 8, and then we have 6, and we have 9, and so on. Is it possible? This is also another possibility. But again, we need to do the in order traversal. So after we find the key, which is 3, so we cannot do this one because we need to find the smallest value of the 3. What is the smallest value of the 3? The smallest value of the 3 is 5. So we need to exchange 3 with 5. That's why now it will be 5 in this position, and then the left will be tilted, and the right will be 8. And the remaining will just still follow the 3. And after 6, we will put another W, which is no. So that's the way to delete where the key is in the internal nodes. So the performance of this tree, okay, it depends on the heat. Okay. So consider an order map with n items implemented by means of binary search tree. So if you still remember in the binary search tree, we have the head. The head, this one. And this is the head. So the space is ON. Okay, means 1, 2, 3, 4, 5. So if we have 5, then the space will be ON or O5. The search and update method takes OH. OH means the head. It depending on how is the head of this tree. The head is ON in the worst case, and it is O log N in the best case. What does it mean? If your tree is like this is binary tree. But when you do the search, you will do 1, 2, 3, 4. So at least you will do n bytes. So you will search this one, you will search this one 2, you will search this one 3, you will search this one 4, you will search this one 5. So it means in the worst case, it will be ON. But if your tree is like this one, then you will get the best case, which is O log N. Once you search this one, and then you check whether it is smaller or higher. If it is smaller, you go to this one, and then check whether it is smaller or higher. If it is smaller, then you go to this one, then it will be only 2 operation, and it will be O log N. So this is the implementation with the tree map. So if your project is related with the map, you can try to use this tree map, and it applies the position with link binary tree. So we need to define what is the key and what is the value. So in this case, we are not using the common dictionary of Python. So you can use the dictionary of Python, but the book authors, they try to develop their own key value. They try to develop their own dictionary. So they have the function to search on the subtree. So this is the function on the subtree. As I mentioned, we can search. If the search from the root, we will check whether it is available with the k or not. If it is not, go to the left. It is not, go to the right. And then we want to check what is the first position of the tree. What is the last position of the tree? Okay, so we can do searching. So the first position means we will check what is the root. For the last position, okay, so we want to check the last position where it is on the leaf. So we have also the before. So it means we will check what is the before of the current position. And what is after? After means I want to find what is the after of the particular node. So there's also another function to find the minimum, to find the greater than equal to, or to find the range. So if I want to find the minimum, you can do searching. You can do searching. Let's say if it is the binary. So the minimum will be on the left part or the most left. Find the greater than or equal to. Okay, so it is just a searching. And then find the range between a starting point until the stopping point. So you can find position. First, you find the start, and then next you find the stop. The remaining is only to get and set. So get means we want to get a value. So it is the find. It is one of the method to find a value. If it is empty, then you will raise an error. If it is not empty, then we call the subtree search. So we will do the subtree search all the time. If the key is not available, then again show the key. Set, it means to insert. Insert a value. Insert a k with a value v. So if empty, okay, then you put directly this new value into the root. If it is not empty, then search. After you search, look at the key, whether the key is already available or not. If the key is already available, then you can just replace the value. If the key is not available, then you can put the value. And then check whether the value should be in the left or should be in the right. Because it is a binary tree, so you need to check whether it is on the left or on the right. The iteration means, yeah, you just need to do the next step until it is finished. The other function, it is about delay, whether you want to remove. So when do you want to remove? If it is in the left or if it is in the right, okay, so you need to check. So this is what we learned before. What is the position of the node? So if there is no leaf, then you can easily remove. But if it is internal node, so it is internal node. If we have left P and if we have right P, so the replacement, it will be using the in-order traversal. This is the in-order traversal. So we want to check the subtree of the last position. It means we want to check what is the minimum value after this value. And then we will do the replacement. Now the parent will have a new parent and yeah, we will remove P and we will rebalance the parent. Delete item, yeah, we just remove the item. If it is not empty, then we will do the search. We will search until we found the value, until we found the K, and then if we found the K, then we remove. So that's about the binary search tree. So we can implement the binary search into the tree. Next, I think we still have some time. Let's go to the priority queue. This is the material for the week 10. So it somehow it is still correlated with the map. So the concept of priority queue, we have the priority queue ADT. And yeah, in this section, we are going to learn more about sorting. So there will be a sequence-based priority queue. So we call the sequence-based priority queue. So we want to search based on sort value. So there will be also the term of priority queue sorting. Priority queue ADT. So priority queue stores a collection of items. And again, its item is a pair. Okay, we use the pair key and value. Key and value. So dictionary, we use the key and value. This is one of the important data structure. So the main methods of the priority queue ADT is to add. Add means insert. We want to insert an item with key K and value X. And we can remove the minimum. It means if we have the smallest key, remove it. Because the word priority. The priority means if we have value, let's say 1, 3, 4, 5, 7, 8, 9. And 1 is the priority. After 1, then we go to 3. After 10, we go to 4. And then 5. And then 7. And then 8. And then 9. So it follows the order. That's why we call it, this is the remove min. We want to remove the minimum value. The additional methods, we will check what is the minimum. It means I want to know only the minimum value, but does not remove. I want to check also what is the length of P and whether it is empty or not. So there are many applications. If you look at the flyers, okay, or auctions or stock markets, okay. So in the auction, it is important because the priority will be the highest price. In the stock market, this is also important. The priority will be, when you want to buy, it will be the smallest price. If you want to sell, then it will be the highest price. So this is an example about the priority queue. So let's say we have the priority queue P and it is empty, starting by empty. Now we will have a new P and V. P, K, and V value. So the key is 5 and the value is 8. So when we insert it, we will have a tuple 5, 9. Now I want to add 9, 7. So 5A, 9C. And then I have another P, which is 3B. So where should we put 3B? Shall we put at the end? Or shall we put at the first? So we will check later. Okay, there are two variants of priority queue. So let's use the priority queue by sorting first. Sorting first means we will put any value in order. So if we know that we have 3, p, if we know 3, p, then we will check. We have 5 and we have 9. Then 3 will be stored in the first one. Now we have 7D. Where's 7? So we need to find out. It is started with 3 and then 5 and then 9. 3 and then 5 and then 9. Then 7 should be in between 5 and 9. I want to check what is the minimum of P. So the minimum of P is 3, P. So we want to check only the minimum without removing. Let's remove the minimum. Then let's remove 3P. So we show the 3P and then now the remaining priority queue will be only 5, 7, and 9. We want to remove the minimum. So we have 5, 2. Then the remaining value will be 7 and 9. I want to check how big is the priority queue. We have 2. And I want to remove the minimum. This is 7, so it goes only 9. And I want to remove the minimum, which is 9, then it is empty. And I want to check whether it is empty. Yes, it is empty. And then I want to remove the minimum error because it is empty. So let's get back about the total order relation. When you have the total order relation, so we need to have the keys. So keys in the priority queue can be arbitrary objects. Arbitrary. It can be anything. It can be random. It can be number. It can be string. It can be name, and etc. On which an order is defined. So you need to define the order. If it is number, maybe 1, 2, 5, 7, yeah, it is easy. But what about if it is a text? Maybe kind of fruits, apple, banana, cherry, and so on. And you need to figure out how to make the order, maybe based on the first alphabet. So two distinct entries in the priority queue can have the same key. So this is something unique because you can have the same key in order to build this data structure. So the mathematical concept, I think I already explained before. So you can refer to this one. It is based on the total order relation. It's just the reflexive properties, which is x is less than x. The anti-symmetric properties, we have x is less than y and y is less than x. It means that x equals to y. If it is the transitive properties, then if it is x, y, and y it is less than z, then we can say that x is less than or equal to. So we can have the priority queue base. We call this is the design pattern. So an item is the priority queue with simply key value pair. So we have a class priority queue base, and then we have a class of an item. So the item, it is a slot with the key and value. So we can do the constructor. Yeah, I hope until now you know the constructor, the key and value. So the priority queue store item to follow for efficient insertion and removal based on the keys. So we can have the LT, or this is less than, and you can check whether the key is empty or not. So there are two kinds of priority queue. So the first priority queue, we call it the sequence-based priority queue. The first priority queue, we call it implementation with an unsorted list. Unsorted. What does it mean? It is not sorted. So whenever you do the insertion, you have a new value 4. Okay, you put 4. And then you have a new value 5. So you put directly after 4. You have a new value 2. Okay, you put directly after 5. You have a new value 3. Okay, you put after 3. You have a new value 1. You put after 1. So the performance is, if you do the addition or if you do the insertion, it will take a 1. Because when you insert, you can insert the item at the beginning or at the end of the sequence. So in this case, if I just put 4 and then I put 5 and then I put 2 and then I put 3 and then I put 1, then it will be 1. However, the remove min, or if we want to check the minimum, it will be ON, right? Because we need to traverse the entire sequence to find the smallest key. So we need to check, is it the smallest No. Is it the smallest? 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 Yes. So it means the big O will be in the worst case ON. Now, the other implementation will be sorted list. So in the sorted list, every time we have a value, we will check. Okay, now I will input 1. Let's say I want to input 5. What is the position? So I need to compare 5 with 1. Okay, 5 is higher than 1. And I will put 1 and then I want to put 4. Okay, then I need to check. 4 is less than 1? No. 4 is higher than 1? Yes. And then I need to check. 4 is higher than 4? 4 is higher than 5? No. Then we will put 1 and then 4 and then. So whenever you insert or whenever you add a value, you will need ON time. Since you have to find the place where to insert the item. So you need to check first where is the position, and yeah, you will put it in the order. So the remove min and the minimum, it will take ON because you already sorted this. So since the small c will be always at the beginning. Okay, so for this code, let's discuss on Monday. Okay, stop here. Any questions? And thank you very much for your